Okay, let's get started. So welcome to Lecture 23. It's great to take the helm again. Thanks, Mike, for holding it off so well. Today we're going to be talking about an entire new topic called synchronous digital systems. As always, we start with a news of the day. There was an article in CACM. By the way, how many of you are ACM student members? Hands up here. We have none of you. Okay, so I'm going to put on my ACM hat now for a moment. I became a student member when I was a student at MIT, been a member ever since. I just became a life member of ACM. ACM is the professional society for anybody in computing field, and student membership is really, really cheap. You get this really awesome magazine as a student. You also get discounts to conferences. I encourage you all to at least go to one conference before you graduate. It really does open your mind to what that is. You get to meet other students interested in that particular topic across the world. So I encourage you to do that, and you should be a student. If you're a student, you get really cheap access to these conferences. Okay, and some of them are even in the Bay Area, so you don't have to travel. You can kind of live at home and go to these conferences. So think about that. Living in a Digital World was a CACM magazine article that talked about what it's like to be in the digital world nowadays for you digital natives. That's all you know. And it says, we're using technology to dial down human contact. There was a movie called Connected, I think we mentioned here. Did we mention the movie Connected in this? Yeah. So Connected talked about that. How many saw Connected? Hands up here with that one. So none of you. Okay, so Connected was a cool movie to see, eye-opening, done by Ken Goldberg and his wife and other, Tiffany Schlein, thank you, that's right. Heavy technology use can result in higher levels of loneliness and depression. Interesting. So you think, well, I'm using technology, I'm using the web, and I'm not connected to everybody. But in fact, the more you kind of disassociate yourself from face-to-face, hand-to-hand, handshake, sit over coffee and talk about things, and the more you put them behind some screen, the more you can go into this kind of well of depression and loneliness. They suggest going offline once a week. And also being present with. If you're ever with somebody, be present with that person and put all your digital devices on sleep away, and don't take a call or a text when you're with somebody. You're talking, and mid-sentence you're like, oh, let me get this. And you're like, I was talking to you. I was telling the story about my mother and the death and the horse fell. No, as a text, how about this cool YouTube clip? That's what they're getting into to interrupt your mother talking about her horse falling on her. Okay, so interesting article. I encourage you to read it. You have access, by the way, to CACM if you're on campus. There's a special deal where you get access to the digital libraries and communications of the ACM, which is this great magazine, if you're on campus. So you should be able to read this URL. Okay. Hello. Again, shout out to anybody watching remotely. I got some email from Daniel Beck from Washington, D.C. So tell Obama to pass the jobs bill, and hello to Daniel. So one of the suggestions, and by the way, one of the things we're going to do this week is get feedback from you, how the course is done. We're sorry that didn't happen before the midterm, but hopefully you're not clouded so much by your delight or sorrow about your midterm grade to be able to give us honest feedback that's not about the midterm, although we would care about that as well. So we're going to show this page every time we kind of switch gears, and this is clearly a gear switching time. Not only are we switching, but the topic is switching. We've talked about these 5 kinds of parallel requests, parallel different angles to this course and to the computing world. And today we're starting all the way at the bottom, which is really cool. And the cool thing about this is you do no work, and the gates just give you free parallelism. Current just flows where current flows, and it all happens all at the same time. So that's kind of cool. It's like, if I'm going to do a rendering, I have to simulate all the electrons bouncing around, all the photons bouncing around to simulate this perfect rendering of this beautiful sunset. Well, it happens for free in the world. Guess what? There's photons bouncing, billions of them bouncing, billions and billions of photons bouncing all around me. No Carl Sagan reference. All right. So anyway, logic gates, and we do that. Again, another high-level slide. You probably saw this. This is the picture where they said this is the old school 61C. But we're going to revisit this in this particular picture to show that 61C, really, if there's one word to summarize 61C, what is it? And don't say parallel. Abstraction. Fun. Fun is a good. I'll take fun. Full credit for fun. Also full credit for the answer I was looking for, which was abstraction. And it's characterized by this. You're sitting up here in this floaty application layer. You don't have any idea how your machine works. It doesn't matter. Abstraction saves you from caring about how things are built, right? That's it. You live in a Manhattan apartment. You live in any one of these guys, and all you care about is providing access, providing a nice API to the guys above you who are going to build things based on you. So you're going to serve as the structural support for them. And you're going to get your stuff working by poking into APIs below you. And that's all you care about is the layer directly below you, like a guy in a Manhattan apartment. And the guy, well, maybe Berkeley apartments. They usually don't go so high and so packed. You use the guys below you, and you provide to the guys above you. OK? So this is how this works. We are literally starting down here. The most important abstraction we've shown here in deep red, should show deep blue, but deep red here is the hardware to software, or I say software to hardware abstraction. That's the most important. That abstraction is worth how much money? Like almost approaching $1 trillion. If you add up all the money in the silicon industry, the Intels, the AMDs, the folks who are building hardware that supports a particular instruction set architecture, the Intel architecture. If you could build a machine that ran on water, that did some amazing things, it was cool, and it was faster than the current model, you would become the richest person around, okay? So this is worth so much money to be able to have that, and you can't have any changes. That ISA is a contract between, blink, a contract between the software and the hardware is this really important instruction set architecture contract. You've learned about the MIPS contract, and that is, I'm going to run, those zeros and ones are the TAL level MIPS. That's that contract. Somebody I'm going to hire to build me a machine, maybe a simulator or an emulator or real hardware to run that MIPS zeros and ones. But that is frozen. It can evolve to the next generation, but essentially that's frozen for that version of hardware and software. You can't make changes around that. That's really important. So here's another view of the same idea. Layers of abstraction. You're living in C, you don't need to worry about compiler world. But now that you know about it, you have much more of appreciation about how stuff works. You can be much faster. You can understand that if Foo calls Bar and Bar calls Baz and Baz calls Garpley, you shouldn't just rearrange the order of your arguments. Because you know in assembly you're going to have to then copy things from A0 to A1 to A2 and back and forth, and that's going to slow you down. Before you knew about assembly, you didn't know about that, right? You now know about how memory is working. So now you understand a little bit below that, and you makes you a better C programmer. Maybe understanding how this stuff is stored makes you a better assembler programmer. People usually don't do assembler programming by hand, but if they did, understanding the layer below helps you. As you keep going down across this big, huge ISA layer, you get down to a block diagram description of hardware that's going to run that MIPS machine. We're going to get to that, but we're going to jump all the way to the bottom and start at the lowest level and work our way back up. So it's almost like a way you take a bite of something. If you didn't have bottom teeth, you kind of have this big layer of meat, and you go, and the teeth would bite to the top. So we kind of went, and now you don't have teeth, so you then flip the sandwich over, and you go, because they're going to no bottom teeth, and then we're going to bite it from the bottom up. So we're going to hit low-level transistor electrons today and work our way back up to this. And at some point, and I hope I'm the guy that's the guy, you're going to bite through, and you will realize your bite has come from the top and has come from the bottom, and you now know how the entire thing works. And I hope I'm the guy to tell you that, because I have this whole cool animation we do. So we'll have a conversation in the back room to make sure they do. It's a fun day. We'll celebrate. It's a great day. OK. So we're starting from the bottom. We're taking a bite from the opposite side of the sandwich today. So we're starting at the bottom. Synchronous digital systems. 3 new words for you, maybe. Synchronous means you have a heartbeat. You're going to have a clock that's going to control that. That's what keeping things in sync. Digital means you have converted all of the world, all of voltages, all of analog ideas, which here is voltages, to ones and zeros. 0 volts is a 0, and 3 volts, maybe 5 in my day, 3 volts in today's day is now a 1. Okay? How about a 2.9? We'll call it a 1. How about 2.5? Well, still a 1. How about a 1.5? I don't know anymore. That's a problem. So we're going to try to have some trouble in the middle, but we're going to try to clean our signals up so we only have things that are close to a high voltage and close to a low voltage. So that's the idea. So we're going to study some logic design. We're going to actually have you work with us as we tell you all the fundamental building blocks of being able to work ourselves up from the bottom so that I teach you all the fundamental blocks to be able to build bigger things on top of bigger things. Again, abstraction layers on abstraction layers. But now we're going from a bottom-up, clearly, model, which is very different than this whole course is. And this is the first day we're ever doing anything in this course from bottom up. Until now, it's always been top down. This is the first time we're starting there. Why do you care about this kind of bottom-up hardware design? Well, there's some exciting courses you might need after that. The most fundamental thing on this list is that we want you, out of graduating 621C, to go from here to here, to understand the entire connection, to bite through the entire sandwich. If you don't understand this low-level stuff, then you say, at some point it gets fuzzy for you. People taking 621A have a fuzzy idea how the machine works. You entering this course had a fuzzy idea of how the machine works. Okay? You're not after this course. If you stay with me and stay with all the lectures and work hard and study, you will get this entire picture. And that's a huge deal when you finally get it. I remember calling home when I got it. When I first got this, I was like, I can't believe I got it. And at some point, that summer, I'm probably stalling this whole thing. But that summer, my best friend, who was a sociology major, said, Dan, can you tell me how computers work? And I went, are you kidding me? You're actually, woohoo! And I said, 2 days, we were on an island, there was no electricity. This is true. And I sat down and I actually explained basically the 621C as I knew it. And I said like, and I went from top down all the way down. I kept going lower, 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 lower. And then you have electrons. It went like, wait, do you realize we just went from, top level, which at the time was whatever C scheme, whatever we were at, to this? And I said, yes, you've done the whole thing. You now, in theory, if you remembered everything, understand the whole thing. And he went like, I can't believe it. I kind of get it. I mean, I'm fuzzy in like 19 places, but I kind of get it. It's exciting. So that's the reason we start at the bottom. That's the key thing here. So, building block. Fundamental building block here is going to be a switch. It's going to be a switch. So let's just look at it without even telling you how we're going to build this switch. This switch can be built out of vacuum tubes. This switch can be built out of water. I don't care. Here's the idea. Here's the abstraction, and then I'll explain how we're building a switch using electronics. I have a circuit. In this case, this again could be water, right? I have a voltage source. I have some kind of a thing here. We're calling this guy a switch, and I have what I hear is a load or a light, okay? When A closes, it completes that circuit, and then current can go all the way around and light my light. So if I close the switch, or if I say A is 1, which means I'm going to close this guy and make A to be 1. 1 means closed, 0 means open or asserted, the light will go on. That's the abstraction level here, okay? When it's open, the current has to go to kind of go in a loop. The current has to return, blah, blah, blah. If you have no loop, then current's not going to flow. This is an open circuit, no lights, okay? So the other side, if it is closed, and then I open it, or I set A to 0, the light stops being lit, okay? It's just the essentials of, this is like minute 1 in EE40, right? This is minute 1 of EE40, okay? So in this way, we're going to say Z, which is my kind of output, here is the load, equals A. When A is 1, Z goes on, and Z becomes 1. The light goes on. When A is 0, which is setting A to 0, moving this to 0, makes the light go off, okay? All right. So now, as I have this switch, I realize I can now wire them in interesting ways. If I wire them here in serial, write this down because that's not on the notes. Serial, that's wiring A serially, A and B serially. I'll give you a second. Not with a C, it's with an S, S-E-R-I-A-L. Then Z has the function of only going on, that light would only go on when they're both closed. When A is closed, 1, and B is closed. Oh, wait, I've heard that before, and. So this is the circuit equivalent of what you have with your ampersand in your C language, okay? This now is an OR. And this is wiring A and B in parallel, which says the current can flow either way. The current wants to get from the left side to the right side, and it can flow either way. So you close either one of these guys, and the thing is happy. If you close them both, no change. It's not like something's better or worse. It'll go either way. It'll divide it both ways, but the point is this guy will be able to get the power coming from the left side. So that's Z or B, okay? So there's AND and OR in circuits. Already we're starting to make connection between circuits and logic gates. You can imagine me giving you a logic gate of an AND and an OR that has 1s and 0s based on this kind of routing, this kind of wiring system. How do we build now? The fundamental question is, what's below this? How do we build a switch out of electronics? Here we go. Gets fun now. The basics are, there's a transistor. If I said this 40 years ago, I'd say the basics were a vacuum tube. But now thankfully, we're out of that era, and we're in transistors. Okay? So typically, we use a technology called CMOS. C stands for complementary. MOS stands for metal oxide semiconductor, on a semiconductor. Okay? There are many different kinds of transistors, but this is the most common. Okay? And they act as voltage-controlled switches, as you saw before. The voltage you're opening and closing is the switch that this transistor is going to give me. This is it. This is the hardest slide of the day, so we'll spend some time on this guy. And I have a movie to help you, because I think movie was worth 1,000 1,000,000 words, right? Pictures worth 1,000, movies worth 1,000 pictures. So I give 1,000 words on one movie I'm going to show you here. I have 3 terminals to this transistor. And these guys are complementary guys. So that means one type is an N type and one type is a P type. And they're just opposites. They're kind of polar opposites. For every good, there's an evil, okay? For every N, there's a P. That's kind of the, you had to have like, whoever ever seen Star Trek, the old show, you got to have the parallel universe with the dagger through the earth and the Spock with the mustache. No, okay, but anyway, there's an evil world in Star Trek you should know about. Nobody's a Star Trek fan. Okay, here we go. So G, S, and D. I remember this by saying, Dan Garcia says it has to be this way. That's how I remember it. All right, but that's how I remember. I don't know. Stands for, that's good stuff, right? Okay, so source, gate, and drain. Here's how this works. If there's no current coming in G, okay? So said another way, if the voltage at G is low, or if G is a 0, right, was what we thought before, then this thing is open. D and S are not connected. If there is a voltage that's higher than the source, or simplifying to saying, if there is any voltage, if there's a 1 at G, D and S go, bink, and are connected. Okay? You turn off G, you turn off any voltage source at the gate, that's why it's called a gate, it opens the gate. When you put some current through the gate, you put some voltage above this threshold, and this now closes. The S to D now closes. That's the digital way we think of transistors. And this is exactly the opposite, by the way. This says it's closed normally. So when this is a 0, this is closed normally. And then when you put some, when the voltage is, when the gate drops below some amount, then it opens. So it's the opposite, right? It's the opposite. This says high voltage, it closes. 0 voltage opens. The P channel says high voltage, it closes. High voltage, it's open. And 0 voltage, it closes. That's what it says. That's what this says here. Okay? So now, let me give you a video that's going to explain the analog side of transistors. Transistors have 2 different modes they can be in. You can operate them in kind of the digital mode, where you're either kind of closing or opening, or you can actually use them as an amplifier. And anyone who's ever had an amplifier has had a transistor in their box. And one of the things you're going to see is the amplifiers usually have a heat sink. So the guys that are used as amplifiers usually have this guy, which is a heat sink. So things that are bigger, the things that look like they would be able to draw heat away from that, are typically used in the analog amplification mode. The guys that are smaller, they don't worry about that because you're just operating at low voltage, typically used in the digital mode. So that's just a little hint, okay? So here is how a transistor, a little 2-minute video I found on the web.
The transistor is like an electronic valve that can be used as an amplifier or a switch. It can control a large current flowing through 2 regions of a semiconductor crystal, like silicon, with a small current applied to a middle region. There are many kinds of transistors. Typical is the bipolar, which has 3 layers: an input layer, a control layer, and an output layer. The layers are either N-type material, which conducts negative charges, or P-type material, which conducts positive charges. The layers are arranged like a sandwich in an NPN or PNP configuration. The individual layers are formed by treating pure silicon with trace amounts of impurities. Adding boron will create N-type material, phosphorus, P-type material. N-type material will have a surplus of electrons, whereas P-type material will have a lack. P-type material has a surplus of electron holes and is therefore positive. The silicon crystal is called a semiconductor because it will only conduct a small amount of current unless a change occurs at the junctions of the layers. In bipolar transistors, the input layer is called the emitter, the control layer the base, and the output layer the collector. When a current is applied to the emitter of an NPN transistor, electrons readily cross over to the P-type base, filling the electron holes. But when these holes are filled, the resulting negative charge repels further electrons that would come from the emitter. The transistor does not conduct. But when a small positive current is applied to the base, it will produce additional holes that will, in turn, allow more electrons to come from the emitter and pass through the base to the collector. Adding more or fewer holes into the base with positive current allows more or less current flow from emitter to collector, like a throttle controlling the speed of an engine. Because the emitter to collector current flow is up to several hundred times greater than the emitter to base current, the transistor makes a powerful amplifier.
So that's the analog side of the world. We treat things in the digital side. So let's actually, get out of this. Hello there. And get back to this. Okay. Release my full screen YouTube. Thank you. Okay. So now, let's actually see how this becomes real for us. Okay? So here is a circuit. I've taken that transistor from this slide. There's an N-type and there's a P-type. Okay? And I've placed two of them here. And I can now say that I'm attaching 3 volts to one end of them. I'm taking X and feeding X in. Here it's the P-type. Remember, this is the P-type with the bubble here. N-type is the kind of normal. And I think of it as normal, and it's negative, but I also think it's normal, okay, which means when current flows, you close. That's how I think of that. Okay, and that's the normal way to do that. And I wire it this way. What's Y's output? So when X is 0 volts, what happens to each of these transistors? Remember, 0 volts is no current, right? Think of that. So what does this guy look like? Normally nothing. If I apply it, does the gate close? No. So this guy is an open circuit down here. It's like I cut that wire. What happens here? By default, 0 volts, what does that do? Closes. So what is Y here with 0 volts? 3. I put in 0, I get 3. Interesting. Now I hope there's going to be a difference, otherwise it's always 3. I might as well just have plugged in Y to the power source, right? Let's see the other guy. 3 volts. And you see how this is wired. It's going to be the opposite of this, right? And this is exactly symmetric in that sense. So I put in 3 volts. This then closes. This then opens. And Y becomes 0. What's this guy known as? An inverter, or not. It's a digital not or an inverter. That's exactly right. You draw this as a big triangle. This is kind of cool. So if this actually were a gate, I'd have a big gate like this with a line and a line, but I have to put a circle here. That circle is the not part. Okay, this is your not. And I would write the word not in the middle if you want to write this up. Okay? This is, and the output is Y, Y, and the input is X. Pretty cool. So there's your first circuit. You now have seen how we go from electrons to a digital circuit. That's closing that last mile. The hardest part of anything is the last mile, right? Oh, I got the internet really close to your house at the transmission station, but getting that last mile to your actual computer is hard. Okay? I can get fiber to your neighborhood, but I can't get fiber to your house. This is like, I can understand my way digitally. How do I make MIPS? I can even build a machine out of ands, ors, and nots. But I don't know how electrons work in that transistor. You now know it. This is that last mile of your understanding. Okay? So we're going from the bottom up. We started electrons flowing, and now I'm at the point I'm in the digital world. From this point on, I'm digital. Let's go another example. Okay? One more before we leave the analog world forever. This is pretty cool. It's nice. There's going to be an analog world coming to visit, again, when we have delays. But in terms of voltages, we're going to leave it for now. Okay? We'll probably leave it, again, from the 61C point of view. So here's my voltage source. Here's the same transistors you've seen before. And now, let's see if you believe me why this guy equals a NAND. Let's see if you believe me. Let's do it together, okay? C is connected to ground when both A and B are 1, right? A and B both close. 1 means closes the gate. Then those wires become firm wires. Then it goes C through A through B's transistors to ground. Now, another problem of wiring these things is you can never have something simultaneously be at voltage source and ground. That's a short circuit. You can't ever take a wire and go, take a wire from 1 and draw it to 0. That can never happen. So you have to have a situation wiring this up that you'll always have, if C is ground, C better not also see the voltage source. So better be, one of those guys better be cut, the wires that connect C to the voltage source. Thankfully, there are 2 of them that can be cut. And guess what? They both better be cut. Because if either one is good, then we're in trouble. Okay? So let's try it. Well, guess what? When these are both 1, these both open up. And it's exactly what we needed. So this is this is an open circuit. There's nothing. This is like a line cutting right through there. There's nothing there. A and B are both open. These are both closed circuits, and C is ground. So the easiest case was the 110 case. But you can also see that if either of A or B were 0, which is the other 3 cases, then C is not going to be ground, right? Because one of those 2 would be cut. So C can't get to ground because both of them have to be 1 to make that line. How about the other 2? can you see that if either A or B has a 0, there's a connection between output and 1? Isn't that kind of cool? So what you're seeing here is an even more powerful idea. We've not only built a NOT, but we've built a NAND, which is a 2-input device, which is harder. I could say, yeah, I got the NOT, but I don't have any idea how to build a 2-input device. There it is. And what's cool about this is the following. Here's the cool line. You agree? Is everybody okay on the NAND? Let me just pause and take a survey. Are we okay on the NAND? Can you get it that explaining to me how on the analog side these things close and open, the voltages work, just so that I actually have this now abstract model of what a NAND is? Are we okay on that one? Because if you say yes, if you're saying yes, then we are officially cutting loose and severing the tie with analog voltages and electrons. We are now in the digital world. If you are comfortable with this, we can go from NAND and work our way up. Okay, you've bitten through the analog part by turning the sandwich upside down, and you're now in pure digital world. And what's so cool about this? You can build ands and ors and NOTs out of only that box, NAND, by being clever about how you wire things together. Oh my gosh. You mean that all I need is this picture, and I can now live in the and or NOT space, and it's going to work? And the answer is yeah. I'm going to leave that as exercise to the reader, and come to office hours if you need help, or ask any TA to how to build an and or and a NOT out of a NAND. But a NAND is your fundamental building block. That's all you need. That's not how they do it. They obviously are more efficient with their wiring to give you an and or NOT. But you could, in theory, having just the NAND as a building block, build everything else above that. In fact, everything we're going to say for the next 4 lectures can be built out of a NAND, because we're going to go from bottom up, okay? That's awesome, folks. This is some really sexy stuff. I love this particular slide, because it really summarizes the departure from needing to worry about analog, and now I'm in NAND, I can do anything from NAND. I'm now that entire mountain of a MIPS machine and a browser is built off of that box. And these 4 transistors, or a lot of them. That's pretty sexy, folks. That's pretty sexy. All right, let's keep going. This is a great day. Okay, so now that I have these devices, I'm now in the digital world, but I still have an analog time. So that's going to get me, okay? So I'm going to have high and low voltages. We're going to say 3 and 0. Again, when I was young, it was 5 and 0, but we've learned that you can control power by lowering your voltages, so they've learned how to redo their circuitry using 3 volts. So I'm going to be able to have, here is what, by the way, a basic clock signal, okay? There's T, which is the period of one clock pulse, okay? From the rising edge to the rising edge, we typically measure that guy. Call that the period, capital T. Frequency is an inverse relationship with period. So time, T is measured in time, so this is in seconds. This would be like 1 nanosecond. And frequency would be inversely related to that, so that's 1 over a nanosecond, which is a gigahertz, okay? That's 10 to the 9th times a second. Okay. Here's what's interesting. Also notice there is not a straight edge here. You know, you draw a clock signal, you always draw a sharp edge. That's not how real world works. The real world does not give you that sharp edge. It gives you a slightly rounded edge, and you try to get it as sharp as you can, but you have to live with what you have. Things can't instantaneously become 1 or 0. There's a little bit of time to adjust for that. So we'll live with that for now, but it might be a problem a little later. In a slide or two, I'll show you that. So the idea is the wire only contains 1 value at a time, and transmission is effectively instant until I tell you otherwise. Here's an example of a box we're going to be able to build together. We're going to build this together in a couple lectures. It's called an adder circuit. I'm going to add A, this should be listed, A and B, and I get the sum out here. I call this an adder circuit. And there's a number of bits that come into this adder circuit. And each of those lines, B0 through Bn minus 1 probably, and A0 through An minus 1, and sum 0 through sum minus 1, look like this. They are really rough. They are wiggly. There's noise in the system. Here's my pretty clock, but my values are not perfect anymore. And you're going to say, well, Dan, if it's going to be this slow slope, at what point does it cross over from a 0 to 1? That really is an issue. But we're going to do the following. We're going to have every single chip, if everybody pitches in and everybody cleans up a little bit of litter, then the whole world will be clean, right? If you picked up more litter than you dropped, wouldn't we do a good job of cleaning up the whole world? Say sure. Okay. What if I built every single circuit, every single block, if the signal comes in noisy, it's going to put out a cleaner signal than it got in. If it didn't do that, then the noise would just propagate. This would go from being kind of a soft rough to being a really slow sine wave to being an ugly thing, and you wouldn't even know where the 0 and 1 starts. So you have the contract that every single piece of hardware tries to clean up those lines and tries to straighten them out. So this was not exactly perfect one. There's not a perfect one, but it tries to clean it up so the output is cleaner than it came in. Because the noise comes in on the lines. The noise doesn't come in here. The noise comes in the transmission lines and all the noise coming in from other devices, right? Maybe the other wires next to it. Maybe the fact that my cell phone was next to my microphone. You heard that go. That's part of it. That's what you're seeing here. That's these wiggles affecting the audio frequency, okay? So each of these black boxes is going to try to clean the deal up. You also have the idea that these 4 lines, that nice nibble of x, in which each of the x's has values, 0 through 1 as this is a 5, 0, 1, 0, 1 is a 5, 0, 1, 1, 0 is a 6, there's an 8, there's a 1, there's a 7. You can draw those like this. You can draw those with a capital X, like a vector, and say this actually represents 4 guys. And you write the number inside, and now all of a sudden this is much easier to write than having to figure out, okay, you're 0, 1, 1, 0, therefore you're a 6. It's much easier to write this as one kind of number and saying, and watch how they write it. Like they write, in this block, kind of make a little bubbly thing, like kind of like a chiclet. That is the value 5. Kind of cool. Okay, so this is just nomenclature and how we write things on timing diagrams. Timing diagrams are going to be your savior if you go into this field. You have to learn to understand and appreciate the value. Timing diagrams are your GDB. Okay? You have a buggy circuit that's not working, you better study that timing diagram to figure that out. And give me some love from Brian and other people who do this for right? Exactly right. All right. So here's an example of a nibble adder. Two 4-bit quantities. I'm going to write those like this. Watch. The wire comes in. I put a little slash, and that means there actually are 4 subvalues, A0 through A3, in that nibble. Isn't that kind of cool? So it's a little cleaner, right, than having 4 and 4 and 4. I just say 1, 1, 1, and with a little slash, it tells you there's a lot of wires there. You're going to thank me when we get to doing a 32-bit data path. 32 lines. No, 32 with one big slash, all right? One line with one slash and a 32 label on the side of it. So A is a vector, B is a vector. Kind of reminds me of the SSE stuff, right? We had vectors you're adding, kind of fun. So A and B are going to add, oh my gosh, here is where the analog thing bites you. And the reality is things aren't perfect. C didn't get to be 5 instantaneously. Look at this. 2 and 3, and then it was 5 for a long time. That was 5. Then A changes to 3, B changes to 3 at the clock pulse. But C doesn't change to 13. C is corrupted. C has the wrong value for a bit of time until C stabilizes. And C stabilizes after what we call a propagation delay. And because this was an adder block, we call this an adder propagation delay. Okay? If there was an OR block, you'd say the OR propagation delay. Okay? And this delay says that you're not going to see the value on the output until some internal time where I stabilize. You can think of this as this box took some time to figure out what the answer was. Let's see, I used to know what 10.3 was. Oh, yeah, 13. That delay is there's a human propagation delay in asking me a question as there is an electronic propagation delay. Okay? Questions so far? So far we don't get to the really hard stuff. What I love about this stuff is this stuff makes sense. This is all kind of, when I would learn this initially, it felt like the person was teaching just to me. I felt that there was no one else in the room, and it was, you ever had that experience with people just teaching just to you? They just teach you the way that you learn best? That's how I learned this stuff. And I just love this stuff because it felt like it all made sense. It always, the question I was about to ask, they said on the next slide. Like it was always perfectly set up for me to feel so comfortable, like a game that's in your zone, right, kind of thing. You guys know. All right. I'm trying to relate to you in a way that you would connect. All right. So here is an example of a piece of software that's going to help you debug your circuit. And look at these guys. Oh, look. Oh, I don't know. 3, 4, 5, like I just said, right? This is a vector that has some number of, I don't know how many bits are on this guy, but there's some variables, and let's explain what this are. Here's how many of this? This is like probably, I'm counting 16 wires there, right? Each of those letters is a hex character that's a nibble, so I'm counting 16 wires on this particular line. You're seeing how there's delays, like this guy rises, and there's a little bit of time before this guy rises, and the next guy goes down. You're seeing this all around. So zoom in on this if you have a chance, and you'll see a lot of delays here. They're not all perfect. Okay? So you're going to need this when you're building these systems, and including when you're kind of even wiring them together. You're going to have to factor that into the whole system. So there are two types the big idea here is that you can divide up the whole world of what I'm going to tell you in the next 4 lectures into 2 types, these 2 types. Combinational logic circuits, which anybody who's a fan of scheme loves this stuff. This stuff says the outputs are a function of the inputs only, just like a scheme function that can't have any side effects and can't have any state factoring into the equation. The outputs are only and purely a function of the inputs, no storage, no past history affecting my output. A state element is the opposite. It says you have some prior history, some prior stored values that are going to affect what you give as your output for a state circuit. Okay? So combinational logic, or CL, and state circuits. And you need both of these guys. You cannot live with one or the other. It's kind of like you have to have both of these to work. State elements without combinational logic, nice, but you can't really do anything with it. And this guy without that means you can't remember anything, so it's not so useful independently. Here's one of the easiest state circuits that you know of in assembler, a register. How does a register work? And inputs and outputs. You have this little triangle guy. This triangle says when that circuit goes up, when that circuit starts at 0 and goes up, here's what the register does. It's kind of cool. Okay? I'm showing you noise. I'm the register. On my outputs, I'm showing you noise. All of a sudden, I get a rising edge of the clock. The register immediately, as fast as it can, turns around, looks at what the input is, and then that's what I have now. It shows us on the output. And we'll hold it there until another rising edge, forever. If there's no more rising edges, if this guy goes up, it stays high. Even if it goes low again, it's still showing you whatever the input was at that moment in time, at that window in time. Like the Wayback Machine. It's the website as of 2006. Here's what it is. Next rising edge, goes around, grabs something, and that's the new value, and holds that until the next rising edge. Okay? So we typically label that as load. Means when load goes high, quickly go around, grab the input, and then hold it, and lock it in there. Until load goes high again, I promise you I will give you that output. That's pretty cool. Clearly a state circuit, right? Input can change all at once, by the way. After that rising edge, input can change all at once. And you might guess that as it turns around, what it hands you better be stable. Does this make sense? Like if I turn around and the value behind you is still forming in the ones and zero-ness, I'm going to grab it, and I'll give you whatever it was. It was supposed to be clean and nice, but there better be stable values on the input during some time before and after that rising edge. We'll get to the details of that next lecture. But that rising edge, there better be stable values. When it turns around, it better say, thank you very much. Here is the data, and here is the data. If it turns around and there's all noise, it's going to be garbage, okay? You have some promises that it needs. There's a spec on this that it needs. What you often do is tie the register to a clock. And then what you have is a guaranteed rising edge every time, and therefore you have a nice little machine where it goes ba-rum, ka-dum, ka-dum, ka-ba-rum, ka-dum, ba-rum, gum, ba-dum, ba-rum, like that. And you have a nice rhythmic pattern where it turns around, grabs some data, and hands it to you in a rhythmic way. And then the whole thing will just work. And we'll see more circuitry that'll do that. That'd be kind of fun. So, clickers, let's rock on that one. We're doing great for time, by the way. Let me also give chance for questions after this, but let me do the clickers, and then we'll have some time. So where is my clickery guy? I had it here. It's here, I think. iClicker. There we go. And we'll have iClicker questions throughout the rest of the 4 lectures. There's this. I'm on the web, so that should just work. And I go here, and I go here. And what we're doing is asking you whether the software can peek past the ISA for optimizations, true or false, or the software can depend past the ISA on a particular hardware implementation, and we'll see how you do on that one. Instruction set architecture. That's the big red slicey thing, the hardware-software boundary. a lot more red seats available here. I'm looking around. Remember we were like packed to the gills? You guys remember at the beginning of the car, with people in the aisles, there was not a single red seat. From my point of view, no red. Turn around, in the front. There's like a lot of red. There's more Stanford than I like. So let's try to get people to come to class, I guess. I don't know what to say about that. We had 291 people in the exam, 291, I think. So that's interesting. Okay. Sorry, sir? They're watching the internet, right? Okay, so let's see how we're doing. Interesting. Interesting. All right, let's pause this guy and talk to your neighbors. This is a good one. Go ahead. All right, let's come back. What do you think? Has anybody heard of the Lollipop page for Facebook? Anybody know that name? Does that ring a bell at all? What's the actual website? What's it called? Try My Lollipop or something? You got to see this page. This is an amazing page. What's the Lollipop Facebook, right? Lollipop Facebook. You need to all visit this page. It's really incredible. It's this, take this lollipop. Take this lollipop. Where's this thing? Forbes. Take this lollipop. No, you need to say, all of you, for fun, take this lollipop, I think it's called. Is that right? Aha, okay. This is it. Okay. Take this lollipop. I encourage all of you to visit this if you're concerned about privacy. Read some of the details of this and take this lollipop and tell me what your reactions are. I'll just leave that there as an exercise for the reader. Okay, so here we go. And stop. Okay, how'd you guys do? Okay, waiting for the web form to close down and iPhones to stop clicking and display. All right, so this is question 2 and question 1. Basically no change. So B is saying 1 is false, you can't peek, but you can depend. That's what B is saying. Anybody want to argue that case? The B, more than half of you. Argue the B case. Cannot peek, but you can depend on what I'm hearing. Give me some love from the B people. Yeah, go. Sure, yeah. Laptop. Okay, so SSD will only run with hardware supports it. Okay. Sorry? The ISA is fixed, though. So I say C. I say the software dynamically, okay, can say, I'm running. I'm live and I'm running. What am I running on? Oh, I'm running on this particular cache size. I'm going to poke inside, see what the hardware is. I'm now going to arrange my data to be faster because I poked and found out what the cache size is. The question is, Can I depend that the cache is going to be configured a certain way? No. If you maintain the ISA, you can build your cache, you can build your stuff any way you want to, as long as you adhere to the ISA. So you can't depend on a particular implementation. That's the whole idea of abstraction. But you can peek to see what the hardware has, to see, I'll do my thing this way for that thing, for this thing, that thing. Do you have 17 math coprocessors? You're not dependent on that. It's not part of the ISA. But if you have them, then I'll maybe rearrange my stuff to pass stuff over there and do the code over there. Do you have a GPU that's really fast? Sure. I'll send my data to the GPU. If you don't, I better still run. You cannot depend on a particular implementation, but you can certainly peek to make use of it. It felt to me like that was a very interesting question that you only got 90% right. I was really surprised with that. Ah, okay, I'm sorry. So if there was a confusion about the wording, I see. You're thinking of the positive spin of can depend. I can depend on this. Well, the particular was supposed to get that in. Like, you really can't depend on a particular thing. The particular is supposed to get you. Like, the way they implement it, that's the particular thing. You cannot depend on how they build it. That's the particular part. You can depend on they successfully adhere to the ISA, but not on the particular implementation. I'm trying to clarify it, so it doesn't matter whether you got right or wrong. There's no points off. But just so you understand that big idea, right? But you can peek at it and see what it is. All right, let's keep going. Sorry if that was confusing to folks, and if you got wrong, the wrong answer for the wrong reason. So here's what's kind of cool. Here's the hierarchy of the whole thing. At the top level is a running MIPS system, people. When this is done, and you understand this, we have closed that loop. You have bitten through the sandwich. We are just beginning to work our way up from switching networks through logic to combinational logic. We'll see more of this next time as we begin to fill this up from the bottom up. In maybe 8 lectures, the whole thing's going to be red circles, and you're going to be comfortable with all those things. So in summary, ISA is the most important abstraction in a computer. It's a $1 trillion abstraction. It's the hardware-software contract. Clocks are the heartbeat of our system. Voltages are analog, but very quickly we quantize those to 1 and 0, and we treat them as 1s and 0s digitally from then on. Circuit delays, as we saw, are facts of life. You have to work those into your designs. And finally, 2 types of circuits, stateless, called combinational logic, and state circuits, which are like registers. All right? Great lecture. We'll see you guys on Friday.